Hello and welcome to Lecture 4 for the course ECE 252B, Spring Quarter 2020. In Lecture 3, we discussed the basics of the addition operation and some simple adders. Today, in this lecture, we will look at a particular class of adders known as Carry-Lookahead adders that are basically the most frequently used implementations of fast adders. Now this lecture is likely going to be a bit longer than the other ones because the chapter has a lot of material. But that's one of the nice things about recorded lectures. I'm not really limited to a particular length of time, and if the lecture is long and you get tired, you can always pause in the middle and continue at a later time. Okay, since we are talking about addition, I thought, for a change of mood, I'll give you a puzzle that involves addition. Okay, so if you have time and you're interested in puzzles, try to work on this one. There are three people, each of which knows a number, let's say the person's age. Call these numbers X, Y, and Z. So three people, each one knows a number, X, Y, or Z. And we want all three of these people to know X plus Y plus Z without knowing the other two numbers. So the person whose age is X, we want him or her to know X plus Y plus Z without knowing Y or Z. So that person will just learn the sum Y plus Z. And similarly for the other three. Each of the three should learn the sum of the three numbers, but not the other two numbers. And we are not allowed to use another person, an arbiter. The three people should solve this problem among themselves. Okay, see if you can find out how they can find the sum of the three numbers without revealing the other two numbers to each person. Okay, so what is a carry-lookahead adder? Let's begin by refreshing our memory about the auxiliary signals G, P, and A. G is generate, so in binary it is XI and YI, the logical AND of the two bits of the operands. PI is propagate, is the logical XOR of the two bits of the operands in binary. Annihilate is the logical NOR of the two bits. And these three signals are mutually exclusive, meaning that one and exactly one of the three is equal to 1. We also define a transfer signal, TI, which is basically GI or PI, the logical OR of GI or PI, or logical OR of XI and YI. And the sum bit in position I is the XOR of XI, YI, CI. So basically the goal of designing an adder is really designing the carry propagation network that gives us all these intermediate carry CIs. And once we know the CIs, we can find sum bits quite easily. Now in an arbitrary radix R, we can still define these auxiliary signals, and basically that's one of the nice things about these signals. If I want to design a decimal adder, once I define these signals GI, PI, AI for decimal arithmetic, then the carry propagation network for the decimal adder is no different than the carry propagation network for a binary adder. Okay, so the problem is the same. So generate signal is 1. The sum of the two digits is greater than or equal to the radix. So for example, when you add decimal numbers, if you add two digits, let's say 5 and 6, the sum 11 is greater than the radix 10, and therefore carry is generated in that position. If the sum is exactly equal to r minus 1, let's say 9 in decimal, then that position propagates carry. And if the sum is less than 9 in decimal, or less than r minus 1 in general, that position annihilates or kills carry. So once you form these auxiliary signals, the rest of the process, the carry propagation process, isn't different from for a binary adder, a decimal adder, a hex adder, whatever radix that you use, a ternary or radix 3 adder, they all use the same carry networks. So at the bottom of this slide, you see the carry recurrence written CI is GI minus 1 or CI minus 1, PI minus 1, meaning a carry goes into position I. So these CIs are what we are trying to determine. So CI is 1 if a carry is generated in position I minus 1, the position immediately to the right, or a carry enters position I minus 1, CI minus 1, and is propagated by position I minus 1. And then we can unroll this recurrence by writing the corresponding expression for CI minus 1. So CI minus 1 is GI minus 2 or CI minus 2 PI minus 2. And if we distribute the expression by removing the parentheses, you get GI minus 1 or GI minus 2 PI minus 1 or CI minus 2 PI minus 2 PI minus 1. And we can continue this unrolling as far as we want. So the last line that you see here, CI is expressed in terms of CI minus 4. We carry 4 positions to the right, and those auxiliary signals. Okay, and this expression is very easy to remember and understand. You don't really have to use the expansion. What this says is that carry into position I is 1 if a carry is generated in position I minus 1, the first term, or a carry is generated in position I minus 2 and propagated by position I minus 1, or a carry is generated in position I minus 3 and propagated by both positions I minus 2 and I minus 1, or a carry is generated in position I minus 4 and propagated by the 3 positions I minus 3, I minus 2, I minus 1, or a carry enters position I minus 4 and is propagated by the 4 positions I minus 4, I minus 3, I minus 2, I minus 1. Okay, it's very logical that carry must have come from somewhere. That somewhere can be position I minus 1, where it was generated, or it could have been generated in position I minus 2 and propagated, or position I minus 3, or position I minus 4, generated in position I minus 4, or it could have entered position I minus 4 and then propagated by all other positions between I minus 4 and I. So this is really the meaning of carry-lookahead. In order to compute CI, we don't really need CI minus 1, CI minus 2, CI minus 3. We can directly look ahead, or actually back, in this case, positions, 4 positions back to I minus 4. And we can compute CI directly based on look ahead to CI minus 4. So given that each carry is a function of all the digits to the right, so for example, carry into position 3 of an adder is a function of x2y2, x1y1, x0y0, and cin, we can directly compute each of these carries by looking ahead to all those digits and then compute the sum. So this will be potentially the fastest possible adder because we don't really rely on the previous carries at all to compute a given carry. So to compute S3, we need C3, but C3 itself is a function of x2y2, x1y1, x0y0, and c0. So if we input all of these values into that box, along with x3 and y3, because S3 also depends on those two digits, then we can directly compute by the fastest possible circuit S3 and S2 and S1. So all of these are computed in parallel without any dependence on each other. However, this is really not an efficient design because as the number of bits increases, those boxes get more and more complex. So let's look at this. So if you have a 4-bit adder, full carry look ahead is quite practical because you can write those intermediate carries in terms of C0. All of them are a function of C0 or carry in. Those various auxiliary generate and propagate signals. And the most complex of these equations is that for C4, which has 1, 2, 3, 4, 5 terms ORed together. And the largest of those terms has 4 variables. That's the last one, C0, P0, P1, P2, P3. So you have a 5-input AND gate for that term and a 5-input OR gate for ORing things together. It's not impractical. Now imagine, so this is basically a 4-bit full carry look ahead carry circuit that gives us C1, C2, C3, C4 based on these expressions. Actually, C4 is not computed based on the expression given on the left, but it's computed based on C3. Okay? I urge you to examine this diagram and understand why C4 is correct. And the reason for that is that C4 being carry out, okay, is a primary output of the circuit, whereas C3, C2, and C1 are not primary outputs. They're further used to compute the sum. So that there's another circuit after computing C1, C2, C3 that gives us the sum bit. Because that circuit is an XOR that has some delay, we can afford to compute C4 by the simpler circuit shown rather than the more complicated circuit indicated by the equation on the left. Because C4 will still be computed in time, correspond to the other output bits, the sum bits. So once we go beyond 4 bits, things become messy. So I can write the expressions for all the carries from C1 to C31 for a 32-bit adder. But look at the expression for C31. That expression has an AND term at the very end. Now this P30, P sub 30 somehow moved to the subsequent line. I should correct this slide. So that term has C0, then P0 through P30. So there are 31 terms. So that's basically a 31 input AND gate. Well, we can't have a 31 input AND gate, so it's an AND circuit. Okay, this delay is more than a gate. And then we also have a 31 input OR gate. Okay, so a lot of hardware is used in computing C31. So C1, C2 are simple, C3 is simple, but as we go towards the higher index carries, the circuit gets more and more complicated, and also will have more and more delay. Furthermore, nothing is shared between these carries, so the complexity of the circuits for the carries adds up. So you have to have 31 different carry circuits. That adds to the complexity. Okay, so here's an example why no circuit sharing is not good. So you have the term C0, P0, P1, P2 computed to form C3, and also C0, P0, P1, P2 appears in that last expression. Okay, given that we don't have a 32 input AND gate, that AND function should be implemented in multiple levels. So perhaps we compute C0, P0, P1, P2, and then AND the result with some other terms and so on. It would be nice if we could share the circuits for that particular term between these two carries. But if we implement them individually, independently, no sharing takes place. So basically, the challenge of Carry-Lookahead adder design is to allow such sharing in order to reduce the complexity of the carry circuit, while at the same time not adding anything to the latency, making it just as fast as this independent parallel implementation. Okay, let me skip the slide. So Carry-Lookahead adders are designed. This is one way to design them. We'll see it other ways later on. By implementing 4-bit look-ahead carry generators. So this block is called 4-bit look-ahead carry generator. Its inputs are a carry in into position I, and G and P signals for positions I plus 1, I plus 2, and I plus 3. So this is a 4-bit block within a longer addition. Okay, it spans positions I to I plus 3. A carry comes into this block, 4-bit block, and we need to produce those intermediate carries. So Ci is known. We want to compute Ci plus 1, Ci plus 2, Ci plus 3. So they are shown in those positions that you see because Ci plus 1 is a function of Gi, Pi, and Ci. Okay, the three signals to its right. Ci plus 2 is a function of Gi plus 1, Pi plus 1, Gi, Pi, and Ci, and so on. And also we want to compute P and G signals for the block of 4 bits. Basically, we want to know whether this block of 4 bits as a whole generates a carry to the next higher block. That's the signal Gi I plus 3, means the generate signal corresponding to the block going from position I to position I plus 3. And then the propagate signal going for the block extending from position I to I plus 3. Now the propagate signal for the block is easy to compute because you see at the top of the slide, Pi I plus 3 is simply the logical AND of Pi plus 1, Pi plus 2, Pi plus 3, meaning that this block will propagate an incoming carry if and only if all 4 positions in the block propagate the carry. If position I propagates, position I plus 1 propagates, position I plus 2 propagates, position I plus 3 propagates, then the carry that comes in basically emerges from the other side. It propagates to position I plus 4. Okay, then the G signal, the generate signal for this block, basically this block generates a carry for the next higher block if position I plus 3 generates a carry. So if the last position of this block generates a carry, that carry will go to position I plus 4. Or position I plus 2 generates a carry and position I plus 3 propagates it, and so on. Very, very similar to the carry, unrolled carry occurrence. Okay, so if I build the circuit and many copies of it, I can use these copies to build an adder in the way that I'll show you. So this is that circuit on the right. And on the left, I've shown you the 4-bit Carry-Lookahead adder that we implemented previously. The circuit, the lower part is similar to what we had in the 4-bit adder. The lower part basically computes the intermediate carries. The upper part computes those block generate and block propagate according to the equations I gave you on this previous slide. Okay, so the propagate signal is a 4-input AND gate. The generate signal is a circuit consisting of 3 AND gates and a 4-input OR gate, which you see in this diagram. So it's direct 2-level implementation of those equations. Okay, so this is a block that is useful in designing Carry-Lookahead adders. Now, if I have blocks, adjacent blocks in an addition, and now these blocks are shown to be overlapping. Ignore those overlap for now. Suppose these are blocks that just touch each other. They don't have to be the same width. Okay, they can be any width. So one block goes, let's say, from position 0 to 8, the other one from 9 to 12, the other one from 13 to 20, whatever. Blocks that are touching each other, but they can have different lengths. Now, each of those blocks has a P and G signal, and there are 4 blocks. Okay, if I have the P and G signal for those blocks, and I have CI0, they carry into the first of those blocks, then I can compute the carries into all the other blocks. And therefore, I can implement this wide adder using smaller adders, blocks with Carry-Lookahead. So each of those blocks has Carry-Lookahead inside. And this circuit at the bottom, the 4-bit lookahead carry generator, is Carry-Lookahead between those blocks. So Carry-Lookahead adders are basically hierarchical, multi-level structures that start with small blocks, then build up to wider and wider blocks until we get to the width that we require for our addition. This will become clear in a subsequent diagram. In fact, right here. So here I've shown a 64-bit Carry-Lookahead adder, the structure of a 64-bit Carry-Lookahead adder. This adder consists of 4 16-bit blocks. The first one on the right, a lot of details inside are shown. The other 3 16-bit blocks are just drawn without any details inside. They're identical in structure to that first rightmost block. Okay, so what is a 16-bit adder block? A 16-bit adder block consists of 4 4-bit blocks and one of those 4-bit lookahead carry generators. Okay, the way this works, I have an animation here. So if you use the PDF version of these slides, this animation is lost. So it doesn't matter. It's not that hard to understand. So let me show you the animation. So initially, let me go back. We have the input signals to those 4-bit adders. Those are known to us. So signals propagate through the first block, which is a 4-bit block that computes P and G for that 4-bit blocks. And the second block, the 4-bit lookahead carry generator, computes P and G for 16-bit blocks. And then finally, that last block at the bottom computes those intermediate carries, C16, C32, C48, so that we have carries to these 16-bit blocks, okay? So this is the first thing that happens in this circuit. Signals propagate through that block, then that carry generator, then this bottom block, and goes, for example, to give us C32. Similarly, C16 and C48. So this is the first part. Now, once you know the carry to the 16-bit blocks, okay, then what happens, I'll show you on the rightmost block. Of course, the rightmost block knows its carry right at the outset, but the other blocks know their carries a little bit later, okay? But what happens inside those blocks is exactly the same as what happens in the rightmost block. So here it is. That carry comes in, it goes through that block, then through this block, then those intermediate carries, C4, C8, C12, become known. And then once C8, for example, is known, that 4-bit adder, which is a carry-lookahead adder, then can compute some bits. So the final part of propagation is from C4, C8, C12 to the sum bits. So if I have a 16-bit carry-lookahead adder, here is an estimate of the latency for that 16-bit adder. I need one gate level to compute P and G at the beginning, and 2 gate levels at the end for sum bits. These are common for all adders, as I said before. So you always start by forming the G and P signals, and you always end by forming the sum bits. So the first number 1 and the last number 2 are common to all adders. Then between these two, we have 2 gate levels for computing the GMP signals for 4-bit blocks, 2 gate levels for computing the block carry-in signals C4, C8, C12, and finally 2 gate levels for internal carries within 4-bit blocks. So the total is 9 gate levels, or more generally, if you had 64-bit carry-lookahead addition, which is 4 times as many as the 16-bit, you add one more of those 4-bit lookahead levels to the tree structure of the previous diagram. So what this slide shows actually is the latency within that 16-bit block on the right, okay? 64-bit adder has another block at the bottom. So one more level will be added, and each level corresponds to 4 gate delays. So roughly speaking, the delay of a carry-lookahead adder built according to this strategy is 4 log k in base 4. So for example, if k is 64, I'm ignoring that 1 for simplicity. If k is 64, log of 64 in base 4 is equal to 3. That's the number of levels in the circuit that we have. 3 times 4 is 12. Okay, 12 gate levels. And this is much less. Remember, if I build a 64-bit ripple carry adder, the propagation will be 64 stages, each 2 gate levels. So it will be 128 gate levels versus 12 here. Okay, so it's a significant speed up. Okay, there's a variation on carry-lookahead addition known as Ling addition. Ling was an IBM engineer who worked in the 1980s in building fast adders for IBM computers. He noticed that a simplification can be achieved in this Carry-Lookahead recurrence by doing the following. Basically, what is the role of all those intermediate carries? We need those carries in order to form the sum bits, okay? The carries themselves are not of interest to us. So if we can propagate some other information that also allows us to form the sum bits, they don't have to be carries, they can be some other information from the stages on the right propagating to the left. And he called that information H, and I sometimes call that Harry instead of carry. So what is propagated from stage to stage is not carry, but it's Harry, H. And HI is defined, if you see on the fourth line of the slide, HI is basically the logical OR of CI and CI minus 1. So it's not CI. We don't inform stage I what the carry into that stage is. We inform it what the logical OR of those two carries, CI and CI minus 1 is. And it turns out, and I let it up to you to study this slide and understand what's going on, the recurrence for HI is a little bit different from the recurrence for CI. Remember, CI was GI minus 1 or CI minus 1, TI minus 1 or PI minus 1. Okay? In this case, is that TI minus 1 or TI minus 1 is replaced by TI minus 2 because of that change that we made. Okay, and this is easily provable. So when I unroll this recurrence, few steps, so compare the unrolled version of the recurrence for HI, which is the next line down from HI, to the unrolled recurrence for CI, you notice some differences. First of all, the largest term in this unrolled recurrence has 4 terms rather than 5 terms in the original recurrence. So the largest AND gate that we need has 4 inputs. And the number of AND gates is 3 rather than 4. Okay? But the number of inputs to the OR gate is the same in both cases, as 5. So the simplification occurs in the AND gates. There's 1 fewer AND gate, and each of the AND gates has 1 fewer input. Okay, so that's basically the source of simplification, which makes the circuit simpler, faster, and more energy efficient. In fact, Link, when he was implementing these adders that he discovered, the technology he used would use wired OR. They didn't use an OR gate. They simply wired together the outputs of those AND gates together to form the logical OR. So in that version, so the advantage of Ling adder over Carry-Lookahead addition, in that wired OR version is a little bit more. That's near the bottom of the slide. So Carry-Lookahead addition needs 4 gates, maximum 5 inputs, of total of 14 gate inputs. So the 14 are a 5-gate input, a 4-gate input, a 3-gate input, a 5-input gate, a 4-input gate, a 3-input gate, and a 2-input gate. The OR doesn't count because it's wired OR. Okay, in the Link version, you have a 4-input gate, a 3-input gate, a 2-input gate. So 9 gate inputs versus 14, which is a significant savings. What you pay for this simplification in the carry propagation or Harry propagation is that the sum expression is a little bit more difficult, whereas for regular carries, the sum is simply the XOR. This is at the very bottom of the slide. The sum is the XOR of PI and CI. In the link adder, the sum is the XOR of PI and the AND of HI TI minus 1. So the sum formation requires an extra gate level, that AND, which was not present. However, this sum formation is done only once, whereas the carry recurrence, implies a lot of circuitry, multiple levels. So you add one gate level at that very bottom of your circuit, but you save many gate levels in the intermediate stages of the carry. So this scheme is known as link adder, and basically many of Carry-Lookahead adders that are implemented today are actually link adders, the link version of Carry-Lookahead adder. Okay, so I still owe you an explanation. Let me go back a few slides. In this slide where the blocks are overlapping, it turns out that if the blocks are overlapping, this scheme still works. In other words, some of the bits are counted as members of one block as well as the next higher block in the overlap region. And if you compute the P and G signals for these overlapping blocks, then you can still combine them in the same way and find those carries that I show there. So the intermediate carries are not into the blocks, but into the non-overlapped part of the block. So you see Cj0 plus 1, C sub j0 plus 1 is the carry into a position of that second block that starts right after the first block. Okay? This is easy to prove, and I leave it up to you to study the textbook to find out why this is the case. Sometimes this leads to optimizations and simplifications to allow overlapping blocks. And I'll show you an example of this later, okay, where that overlap, it seems that the overlap is really inefficient because you're dealing with bits more than once inside one of the blocks and another time inside the next higher block. So that might seem that leads to inefficiency, but it does lead to efficiencies in some cases. Okay, so that 4-bit look-ahead carry generator can combine information from either adjacent blocks, touching blocks, or overlapping blocks. I've two of the blocks here, two of the pairs of blocks in this example are overlapping, but that doesn't cause any problems in using this 4-bit look-ahead carry generator. By the way, 4-bit is not a magic number. You can design a 3-bit look-ahead carry generator or a 5-bit. Okay, but experience has shown that with 4 bits, 4 input gates are easily built. They're slower than 2 input gates. Okay, but not by much. But if you go to 5 and 6 input gates, then they start to become much slower. So that's why 4 is used as the blocking factor. And besides, 4 being a power of 2 is convenient because a 64-bit adder can be divided into 4 16-bit blocks, and a 16-bit adder can be divided into 4 4-bit blocks, whereas 3 would not be as convenient. Okay, so let's now go to the next stage of our discussion, where I introduce a different way of viewing and designing carry-lookahead adders. And these are known prefix adders or parallel prefix adders. Those of you who have taken the parallel processing course know what parallel prefix computation means. So I'm going to define it. Don't worry if you haven't taken that course. So here I've shown a 2-input version of that carry-look-ahead block. So the blocking factor is 2, which is still convenient because if you design a 2-bit adder, then you can go to 4-bit adder, then to 8-bit, then to 16. You will have more levels. But given that each of these blocks deals with only 2 bits, okay, it can be faster. So you can recover some speed, even though you will need more levels of blocks. Much of that lost speed because of more levels is regained because the blocks are now much simpler and faster. Okay, so I've shown here what I call the carry operator. That circle with a send symbol inside. So that send stands for carry operator. And carry operator basically takes the P and G signals for 2 blocks, P prime, G prime for 1 block, and P double prime, G double prime for another block, shown on the left. And these blocks, again, can be overlapping. They can be touching. And then it produces the P and G signal for the overall block. That in this example goes from position I0 to position J1. So one block goes from I0 to J0. One block goes from I1 to J1, and they may be overlapping. And the overall block goes from position I0 to J1. And at the bottom of the circuit on the right, you see the expressions for those 2 outputs. The block as a whole propagates if both of those smaller blocks propagate. So P is equal to P prime, P double prime. And the block generates a carry okay, sorry, there's an error in that expression. That G prime should be G double prime. So a block generates, I'll correct this later. I can't correct as I record this lecture. So G is G double prime or G prime P double prime, meaning that the block as a whole generates a carry if that upper block generates a carry, G double prime, or the lower block generates a carry, G prime, and the upper block propagates it, P double prime. So that box that you see at the bottom is that carry operator. It has 4 inputs, P prime, G prime, and P double prime, G double prime, corresponding to 2 touching or overlapping blocks. And it gives you the P and G signal for the overall block. And the logic implementation of that carry operator is this very simple circuit. So the AND gate at the bottom produces the P, which is P prime and P double prime. And then the other 2 gates AND and OR produce G, which is G double prime or G prime P double prime. Okay, so that circle with the cent inside is a shorthand notation for this 3-gate, simple 3-gate circuit. This is basically a look-ahead carry generator for just 2 bits. Okay, so the carry computation problem is given G0, P0, G1, P1, the GMP signals for various positions. Notice that these are written now in the opposite direction of the standard direction. Normally G0, P0 will be all the way at the right, Okay, and so we proceed from right to left. I've written it from left to right for reasons that will become evident shortly. And then my goal is to evaluate those block GMP signals that's shown. G00 means the block of bits extending from bit 0 to bit 0. So it's just one bit. G01 means block of bits extending from bit 0 to bit 1, so that's 2 bits. And G02 will be 3 bits. Until all the way at the right, we have G0K-1. That's basically K bits, the generate signal for the block of all K bits. Okay, so if I have all these values that I've shown there in front of find, then C1 is basically G00. I'm going to assume that there's no carry in, okay? There's no C0. C0 is equal to 0. So C1 is 1 if a carry is generated by position 0. So C1 is the same as G00. C2, carrying to position 2, is 1 if position 0 and 1 collectively as a block generate a carry. So C2 is the same as G01. CK-1 is G0K-2, and CK is G0K-1. So basically, if I compute, given those G and P signals for individual bits, if I compute the G and P signals for successively wider blocks, 1 bit, then 2-bit blocks, then 3 bits, all the way to K bits, then I have all the carries that I need. If I do have carry in, then I can basically view that as another position to the right, or to the left in this case, because I'm starting position 0 at the left, position -1. Carry in is the generate signal for that position -1. In other words, if carry in is equal to 1, it's as if that position -1 generated a carry for me. And P-1 is always 0. Okay, so these desired pairs that I see up there that I want to compute, look at this expression here. G0, P0 at the middle of the slide. G0, P0, carry operator, G1, P1, carry operator, so on until GK-2, PK-2, GK-1, PK-1. If I compute all the prefixes of this expression, okay, these are the prefixes. G0, P0 is the same as the first pair of bits that I'm trying to compute. So there's no computation involved there. Then G0, P0, carry operator G1, P1 gives me that second pair from which I derive C2. Okay? So basically, finding the carries is the same as computing all the prefixes of this expression. This is why the computation is known parallel prefix computation, because I want to compute all those prefixes in parallel. Of course, those prefixes can be computed serially. First find G0, P0, then compute G0, P0, carry operator G1, P1, and so on. That will be ripple carry, okay? I want to compute all of these prefixes at once. Now this carry operator is associative, meaning that it does not matter. So if I'm trying to compute the prefix consisting of the first 3 terms, G0, P0, G1, P1, and G2, P2, or G1, P1, G2, P2, G3, P3, okay? It doesn't matter whether I first combine G1, P1 with G2, P2, and then the result with G3P3, or combine G2P2 with G3P3 over here, and then combine that result with this one. So I have some flexibility in the order of performing these operations because the operation is associative. However, the operation is not commutative. So for example, if I want to compute this whole expression shown in the middle of the slide, I can't go ahead and first combine G0, P0 with maybe GK minus 1, PK minus 1 at the end, and then combine the result with this term, and then I can't change the order of things because the operation is not commutative. They have to be performed in the order shown, but I can group the terms together in different ways if that makes the computation more efficient. Okay, now rather than continue with the discussion of parallel prefix computation with the carry operator, which is a little bit less intuitive because it involves operands that are pairs of bits, in an operation that is fairly new to us, and we may not yet be, very comfortable with how it's applied, I'm going to use addition. So basically, instead of parallel prefix carry operation, I'm going to perform parallel prefix sums. So I'm going to assume that these x values are, let's say, integers or numbers. And I'm interested in finding x0, the sum of the first two numbers, the sum of the first three numbers, and then the sum. So this is known as parallel prefix sum. Now, any circuit that computes these sums using adders, this plus sign represents adders, can be converted to a parallel prefix carry circuit by replacing the inputs, which are integers in this solution, with these pairs of bits, and the addition operator with carry operator. With one provision. Addition happens to be commutative, so it doesn't matter whether you compute x0 plus x1 or x1 plus x0, okay? But it does matter whether you compute G0, P0 carry operator G1, P1 or in reverse order, okay? So as long as we keep the ordering intact, any circuit that computes these prefix sums for us can be converted to a carry circuit, by simply replacing the adders with carry operators and the integer inputs with these pairs of bits. So this will become clear. So this is a parallel prefix sums circuit for 4 inputs. So inputs from the top are 4 integers, and outputs at the bottoms are partial sums. So let's say the numbers are 5, 2, -1, 6. I've basically reversed again the direction. The first number is 5. So really what I'm doing here, I'm computing postfix sums, not prefix sums. This corresponds, more directly to addition because bits are usually shown from right to left. Least significant bit, then the next least significant bit, and so on. So what I want this circuit to compute are 5, 7, which is 5 plus 2, 6, which is 5 plus 2 minus 1, and 12, which is 5 plus 2 minus 1 plus 6. And this circuit of adders does this for me. Input adders. First of all, because the last output is the sum of 4 numbers, and I have 2 input adders, no matter how hard I try, I will need at least 2 levels of adders in my circuit. And this circuit actually uses 2 levels of adders. So I can't do it with fewer than 2 levels of adders. or log base 2 of 4. Okay? So it's the fastest possible circuit, but it does some sharing. Notice that the circuit that computes this circuit, it computes the number 7, also contributes to the computation of this number 6. So I'm not computing this number 6 directly based on these 3 inputs, but I'm taking advantage of this partial sum computed there. And I do that because it doesn't add to the delay. I need 2 levels of adders anyway. So here also I have 2 levels of adders, so it doesn't increase the delay of this parallel prefix sums circuit. So I can convert this into a 4-bit adder directly. Those numbers at the top are replaced by PNG signals. The adder circles are replaced by the carry operator. And at the bottom, I get PNG signals for successively longer blocks. And once I got those, G00 is C1, G01 is C2, G02 is C3, G03 is C4. So at this last level, I don't really need this P01, P02, P03. So the circuits corresponding to forming those can be removed. But this is cleaner. We always deal with pairs of signals. PNG for bits, shown at the top. PNG for a 1-bit block, for a 2-bit block, for a 3-bit block, for a 4-bit block at the bottom. And I've computed the carries. Okay? So from now on, we're going to think in terms of parallel prefix sum circuits because they're much more intuitive. Remembering that we never reverse the direction because addition is commutative, but the carry operator is not. Okay, I have to combine things in the same direction. So this one with this one. Okay, this one, the combination of those two is combined with the third one. The order is maintained. Okay, this is to the left of those other two. Okay, now that we learned the correspondence between the carry problem and parallel prefix addition, we can do a whole bit of interesting things. So parallel prefix computation first was studied by researchers in parallel processing, not in computer arithmetic. And later, computer arithmetic researchers basically realized the correspondence between these two, and sort of they took designs produced for parallel processing and converted them into adders. So this first design is due to Latner and Fisher. They were parallel processing researchers. It's known as the Latner-Fisher network. It says to compute the parallel prefix sums for k numbers, let's say k is even. Compute prefix sums for the lower half of the numbers, x0 through xk over 2 minus 1, and for the upper half, and then add the sum of all numbers in the lower half to each of the prefix sums for the upper half. And this gives you the correct prefix sums for the upper half. So the lower half is computed directly by that half-size circuit, and the upper half needs that half-size circuit plus a bunch of adders at the bottom to complete the process. So this is known as Latner-Fisher parallel prefix sums network. Now, if I try to convert this to a carry network, I run into this problem that signal, the last signal from the first block, from the right block, has a large fan out because it feeds a whole bunch of carry operators on the left. So it's not directly implementable as a logic circuit due to that large fan out. But let's ignore that for now. So the question is, how fast is this and how much circuitry does it use? we can use recurrences to evaluate that. So the delay of the circuit is the delay of that half-size circuit. So it's a recursive construction. Okay, so whatever the delay of this half-size circuit is at the top, I have to add 1 unit. I'm assuming that this addition or carry operation takes 1 unit of time. So d of k is d of k over 2 plus 1. And the solution to this recurrence is log 2k, which is the best speed possible. If I have k things to combine, because this last output is a function of all those k inputs, I need a minimum of log 2k levels of these additions to compute that, so the delay is optimal in this circuit. The cost of this circuit, ck, is twice the cost of the half-size circuit because I have 2 copies of that circuit, plus k over 2. And again, I'm assuming that these adders have unit cost. So 1 unit of cost there for each adder. So k over 2 units of cost for all of them. And the solution to this recurrence is k over 2 log k. So this design has logarithmic delay, and the best logarithmic delay, the constant in front of it is 1. And it has k order k log k cost. Now, remember that the ripple carry adder has linear delay, order k delay, so it's much slower than this, but it has order k cost, so it's cheaper than this because we use k full adders. Each full adder has a constant cost, so it's an order k cost. So the ideal would be if we can achieve this minimum delay of log 2k with the minimum cost of order k. And at this point, we don't know whether that can be achieved because this attempt gave us the best possible speed, but not the best possible cost. Okay. This is a second design known as Brent-Kung parallel prefix sums network. Brent and Kung were researchers in the area of VLSI who were interested in designing efficient adders. So they came up with this design. So what is this design? It says if you want to compute all the prefix sums, add pairs of numbers, x0 and x1, x2 and x3, and so on. Again, I'm assuming k is even. And then these sums of 2 numbers, x0 plus x1, x2 plus x3, and so on, are fed into this prefix sums circuit, which is half the size because there are half as many of those numbers as there were inputs. All the other lines go through, okay? They don't connect to that box. So half of these lines connect to that box, and these are prefix sums computed based on those numbers that are, each of which is the sum of 2 numbers. So basically this output, the first output of that box, will be x0 plus x1, which is the first input of the box. The second output of the box will be the sum of this input and this input, which is x0 plus x1 plus x2 plus x3. So half of the outputs that I need are already formed by that box, S1, S3, all the odd index outputs. And then the even index output like S2 can be computed by taking S1 and adding x2. S4, I take S3 and add x4, and so on. Okay, please study this and make sure that you understand why this provides the outputs that we are seeking, the correct outputs. So these are the recurrences characterizing the delay and cost of the circuit. The delay is the delay of this half-size circuit sitting in the middle, plus these additions at the top and these additions at the bottom, plus 2 units. 1 unit at the top, 1 unit at the bottom. And if I solve this recurrence, the solution would be 2 log 2k minus 1. Actually, we will see later that it's minus 2. There is a subtle point there that makes it minus 2. But let's not worry about that difference. So it's 2 log 2k roughly, twice as much as the previous design, Ladner-Fisher design. The cost recurrence is ck minus 2, the cost of this half size, plus k minus 1. There are k minus 1 adders. Notice that each of the vertical lines has an adder on it, either at the top or at the bottom, except for this rightmost line. So there are k lines, all but one of them have an adder on them, so k minus 1. So the solution to this recurrence is 2k minus 2 minus log 2k. So again, ignoring minus 2 and minus log 2k, those small terms, this is 2k. So the cost is linear, which is good. The delay is logarithmic, which is good, but is not as good as the previous design. But the previous design was not a real design anyway, because that fan-out problem made it not suitable for direct implementation. Okay, so Brent and Kung designed an adder that has both logarithmic latency, and linear cost. So it's pretty efficient. So this is Brent-Kung carry network for an 8-bit adder. So you notice that it's a recursive construction. So this, inside this dashed box, you see a 4-input Brent-Kung network. And these are the adders we saw at the top. And these are the adders we saw in the previous diagram at the bottom. Each of the adders is replaced by a carry operator. Okay, and here you see, we said there's 2 log k minus 1. In this case, 2 times 3 minus 1, it should be 7. But it's really, 2 times 3, which is 6, minus 1 should be 5. But it's really 4. Okay, there are 4 levels of add. The reason is that when you solve the recurrence, these two carry operators or adders in the previous design count as separate levels, because this is basically the top part of the circuit, and this is the bottom part of the circuit. But it turns out that the operation of this block is independent of this block, so we don't need to count them as separate level. They're one level. So the solution to that recurrence is 2 log 2k minus 1, if we just solve it mathematically. But in practice, it's 2 log 2k minus 2, if we observe that 2 of these circuits can be placed on the same level. Their latencies do not add. This is Brent-Kung network for 16 bits. Again, you see the 8-bit network sitting in the middle, and then there are the adders at the top and the adders at the bottom. And the 8-bit network itself has a 4-bit network. Okay, here's another design. Now somehow all of these designs are associated with 2 names because the research or the papers where they were introduced have 2 authors. This one is called Kogi-Stone parallel prefix graph, or parallel prefix network. Okay, this one also starts by pairwise additions, whereas in Brent-Kung network, we added x0 and x1, then x2 and x3, then x4 and x5. This one also adds x1 and x3, okay, x4 and x5, so it does more additions at the top. All pairs, all adjacent pairs are added to each other, not just x0 and x1 and x2 and x3, but also x1 and x2. And then so the pattern here is that the top row is missing a circle here at the right. The next row is missing 2 circles. The next one 4 circles. And then the next one 8 circles. So that's the pattern. And then the connections to these circles comes from 1 position to the right at the top row, from 2 positions to the right, from 4 positions to the right, and from 8 positions to the right. Okay? So again, I leave it up to you to study this and convince yourself that it actually does compute the prefix sums that we are interested in. So here are the costs. Well, the delay, first of all, is log 2k, 4 levels for 16 bits. Okay, so it's the best possible. The cost formula is basically that summation. K minus 1 adder at the first level, K minus 2 at the next level, K minus 4, K minus K over 2 at the last level. And if we add all of those, do the math, it becomes K log 2K minus K plus 1. Again, if you ignore minus K plus 1, this is order K log 2K. So it's more expensive than the Brent-Kung design, but it's faster. It's as fast as Ladner-Fisher design, but doesn't have its fan-out problem. Notice that each of these signals goes at most to 2 places. So for example, this signal over here goes to the output and also goes to this circle over here. So it's as fast as Ladner-Fisher without its fan-out problem. So the fastest adders can be built using this network. So here you see the comparison of the 3 methods that we discussed so far. Ladner-Fisher, log 2k delay, K log 2k cost, Kogi-Stone, log 2k delay, K log 2k cost. So the two are comparable in terms of delay and cost, although the Kogi-Stone design does not have the fan-out problem. And Brent-Kung is roughly 2 log 2k, 2 log 2k minus 2 to be exact, so higher delay, but lower cost, linear cost. Okay, actually we can reduce the cost of Ladner-Fisher to linear using some tricks that are illustrated here. I won't go into the details. The basic idea is that in this block, this is the Ladner-Fisher design. In this block on the right, we should strive to produce this signal in minimum possible time because it has to go through additional circuits before it gets to the output. Whereas all the other outputs of this block on the right, we have 1 unit extra time to produce them. If you produce those a little bit later, okay, it doesn't matter. 1 unit later, it doesn't matter because by the time these signals are obtained, these are also derived. So that extra flexibility in generating these signals a bit later allows me to simplify the circuit just enough so that the overall cost goes to linear cost. But still, the fan-out problem is still there, so I won't dwell on this change, simplification. So let's look at these 2 main networks that we derived. For 16 inputs, Brent-Kung on the left, Kogi-Stone on the right. You can see by just looking at these that the Kogi-Stone circuit is denser. It has more circles more adders, more carry operators, and more wires. Brent Kung circuit is sparser. Okay, Brent and Kung were interested in efficient VLSI implementation so that the adder did not take up much chip space. So that's why they produced that design. So to compare these two, it's 6 levels versus 4 levels. Kogi Stone is faster by 2 levels. And 26 cells versus 49 cells. And I'm not comparing the wiring. Okay, the wiring is also denser for Kogi Stone. Even ignoring the wiring, still the Kogi Stone circuit is much more complicated. Now, interestingly, we can design a hybrid adder that combines the ideas of Brent Kung and Kogi Stone. So it starts with Brent Kung at the outset. So we combine pairs at the top row. We combine pairs of numbers using these adders. And at the bottom, but instead of using an 8-input Brent Kung in the middle, I use an 8-input Kogi Stone circuit in the middle. So I'm combining both ideas. I start with Brent Kung at the top and bottom, and then instead of going to an 8-input Brent Kung, I use an 8-input Kogi Stone, which has a delay of only 4 instead of delay of only 3, 3 for 8 input. So this gives me a hybrid design with 5 levels and 32 cells. So provides a good trade-off. So I shaved 1 level off the delay while adding only 6 cells to the design. I went from 26 to 32. Okay, so there are a lot of possibilities for these hybrid or intermediate designs. So if I have 64-bit inputs, for example, I could do 1 level Brent Kung and then switch to Kogi Stone. Or I can do 2 levels of Brent Kung and then switch to Kogi Stone, providing various design points, various trade-offs in speed and cost. By the way, this is known as Hahn-Carlson design. Hahn and Carlson were 2 authors who first proposed this type of design. Okay. Now, in designing a Carry-Lookahead adder that is 64 bits wide, I need all the carries C1 through C63, all the intermediate carries. However, there's a design strategy that allows me to bypass some of those, not generate them, and we'll see more details later. Here I'm aiming to derive just these intermediate carries, C8, C16, every 8 bits. C0, of course, is known at the outset. I'm aiming to compute C8, C16, C24, every 8 bits, C32, C40, C48, C56. Okay, how do I go about this? Well, I can design Manchester carry chains that are 4 or 5 bits wide. Okay, the Manchester carry chain on the left is 4 bits wide. P0, G0, P1, G1, P2, G2, P3, G3. And it computes for me these P and G for the 4-bit block. So I call this the Type A Manchester carry chain. By the way, this design comes from an actual adder designed for a microprocessor and introduced in this reference, Lin C92. It's a 1992 paper. So I've grabbed these designs from that particular paper, and that was an AMD microprocessor. Okay, so that's a 4-bit Manchester carry chain that gives me P and G. So you can see here that, see, if P0, P1, P2, and P3 are 1, all these 4 transistors will conduct, and therefore P03 will be asserted. And similarly, the G signal. Now this one is similar, a slightly different version, the type B Manchester carry chain. It still receives the same inputs, P0, G0, P1, G1, up to P3, G3. It computes the 3-bit block P and G, but also these smaller blocks. So, sorry, the 4-bit blocks, 0 to 3, the 3-bit block 0 to 2, and the 2-bit block 0, 1. So these intermediate values are also computed, so it uses more of these CMOS transistors to yield that. Okay, so suppose I have these type A and type B Manchester carry chains as my building blocks. Then I can use them in this circuit to compute, so this is a Carry-Lookahead circuit, to compute C8, C16, C24, C32, and so on in the following way. So there are 16 type A blocks here on the left that give me PNGs for 4-bit blocks, okay? 0 through 3, 4 through 7, 8 through 11. So these are 4-bit blocks. And each of these lines represents 2 signals, the P and the G, for that group of bits. Now here I have a type B Manchester carry chain that takes P and G for block 48 to 51, block 52 to 55, block 56 to 59. These are adjacent blocks, touching blocks, 60 to 63. And it gives me P and G for the total block 48 to 63, but also intermediate one, 48 to 59 and 48 to 55. Those two are not used, but this one is used here, 48 to 55. This is another type B Manchester carry chain. By the way, the carry in is introduced as an extra line here, bit position -1 to -1. So this type B Manchester carry chain is a bit wider, 1 bit wider. It has 5 inputs as opposed to 4, but it's the same idea. So this one basically, this output will be from -1 to 7. The next output would be from -1 to 11. And the next output will be from -1 to 15. And then if you follow through here, you see that all the carries that we require, C0, of course, is an input, C8, C16, all the way to C56 are derived with 3 of these blocks on the critical path, a type A block and 2 type B blocks. And this design is where that idea of overlapping blocks was introduced. So if you look here, these 2 blocks are overlapping, and it actually leads to 1 fewer level of these boxes. This block 16 to 23, and this one, instead of being 24 through 31, is 16 to 31, because that is available from here. Whereas 24 to 31, I need additional hardware to generate. So again, the outputs of this block will be -1 to 23, -1 to 31. Doesn't matter that these two are overlapping. And -1 to 39. Okay, so this is the carry network used for that AMD microprocessor. It's a 64-bit adder. This is just the carry network. But this by itself is not enough because we are still missing some of the carries that we require, okay? We don't have C9, C10, C11, and so on. We just have these 8 carries. I'll show you at the end of the next chapter how we fill the gap and basically find the sum of the two numbers without actually generating those intermediate carries. All right, so next time we'll deal with the variations in fast adders, a bunch of different designs, as well as a completion of this adder, for which we have a partial carry network already designed here. And then chapter 8, after that, will be multi-operand addition. Okay, take care until the next lecture. Bye.